Welcome everyone for this edition of the Brazilian Algebraic Geometry Seminar. Today we have Douglas Guimarães, which is a PhD student here in Campinas, just back from a period at the University of Portland in Dijon. And he'll talk about the moduli spaces of quasi-trivial rank 2 sheaves on P3. Douglas, please go ahead.
Okay, thank you for the invitation. Thank you for the opportunity to speak here. So I'm going to talk a little bit of my PhD project with Marco Giardini and Daniele Faenzi. So I'll talk about a moduli space of quasi-trivial rank 2 sheaves on P3. So let me begin by fixing the notation and explaining what do I mean by these quasi-trivial and these moduli spaces of these guys here. So for every coherent sheaf on Pn, we have this canonical map to its double dual, and we say that E is torsion-free if this map here is injective, a monomorphism. So if this map is an isomorphism, then we say that E is reflexive, and by quasi-trivial, I mean a torsion-free sheaf, which is its double dual is just the trivial bundle, where this R here is the rank of E. And since E is a subsheaf of this double dual, we can make the quotient, and we ask this quotient to have dimension 0. So this is what I mean by quasi-trivial. And this nomenclature was borrowed by Artankin, where he studies these sheaves and so on. So the other word here in the title is the moduli spaces. To talk about moduli spaces, we need this notion of stability. So let's talk a little bit about the notions that we are going to use in this talk. So for a torsion-free sheaf on Pn, we can define this mu of E as the first Chern class of E over the rank of E, and this little p of E by the Hilbert polynomial of E over the rank of E. And this is called the slope of E, and this is the reduced Hilbert polynomial. And with these two guys, we can define what the notion of mu-stability and semi-stability. So we say that a sheaf is mu-stable if for every non-trivial subsheaf of E with less rank, we have this inequality holding. So we say that E is mu-stable if the inequality holds here for every subsheaf of E. And if we allow equality, then we say that E is mu-semi-stable. And this is usually called the slope stability. And when this holds for the reduced Hilbert polynomial, we say just E is semi-stable, and can be known also as the Gieseker stable. Again, for inequality, we say that it's stable, and for if we allow equality, we say that it's semi-stable. So using this, relating these two notions of stability, we have this chain of implications here that mu-stability implies stability, which implies semi-stability, and finally mu-semi-stability. We'll use this chain of implications later. So the main moduli space that we are going to treat in this talk is this guy here, the moduli space of semi-stable rank R sheaves with Chern classes C1, C2, and C3. This is the first, obviously, second and third Chern classes. And Murayama showed that this moduli space is a projective scheme, and since then, many authors try to answer geometric properties of this space. For instance, when the rank is 1, we can always twist this C1 to ensure that C1 is equal to 0, and then this moduli space becomes the Hilbert scheme of one-dimensional subschemes with given degree and genus by these C2 and C3. And this Hilbert scheme is known to be always connected by Hartshorne. So we could ask ourselves, what happens is this moduli space when the rank is higher, always connected as well? So many authors try to answer these properties. For example, and for the rank 2 case, we have results about irreducibility or the number of components of this moduli space, especially for these low values of C1, C2, and C3. But the main case that we are going to treat here is this guy here. The rank 2 semi-stable torsion-free sheaves with C1 and C2 equals 0, and C3 equals minus 2n, where this n is some positive integer. Here it's enough to consider only negative third Chern classes. And since it only depends on n, I'm going to denote this by nn for now on. And what we are going to do here, we are going to construct an irreducible component for this moduli space here. And we are going to show that for low values of n, this is the only one. That is, this nn is irreducible, and we have this, in some sense, description of our moduli space given by this component. And to achieve this result, we're going to treat these sheaves in two different ways. We are going to view these sheaves as first as points in the Quot-scheme. We are going to relate with some points in the Quot-scheme. And second, we are going to relate with extension of sheaf of ideals. So let me begin by stating these two viewpoints, and then we can move on to the moduli space. So what do I mean by a point in the Quot-scheme? So I always denote this by some phi and q. So phi is a map from first the Quot-scheme. It's a fine moduli space. It's a projective scheme shown by Grothendieck that parameterizes quotients of a given sheaf with a given Hilbert polynomial. So in this case, our sheaf is just two copies of O. Just for notation, I will always work over the complex numbers here. And the Hilbert polynomial is just a constant equals to n. So to say that it's a quotient means that this morphism is surjective, and this Hilbert polynomial of Q is just equals to n. What we can do now is consider the kernel of this map, and let me call this E. And so with this E, we can compute its Hilbert polynomial and these Chern classes, and we see that C1 equals 0, C2 equals 0, and C3 equals minus 2n, exactly like we wanted. So the first result that we are going to prove here is that this, for every point in the Quot-scheme, this kernel here is always μ-semistable. So this is stated here. Let me try to give you an idea of this proof. So as before, we have this short exact sequence here, and we are going to dualize this sequence. That is, we are going to apply this home sheaf to this sequence, and we are going to arise in this other sequence. Of course, this other sequence goes on, but we only need this piece here. So since Q has dimension 0, this Q dual here is 0, and this X1 is also 0. And so we have this isomorphism in the middle here. And since this E dual is isomorphic to two copies of O, and since two copies of O is μ-semistable, this implies that the dual of E is μ-semistable. And since the mu stability behaves well with the duality, this implies that E is also μ-semistable like we wanted. So what we have here, we have that this, for every point in the Quot-scheme, the kernel has Chern classes 0, 0, minus 2n, and it's always μ-semistable. We can ask if the converse is true. So if every μ-semistable with Chern classes C1, C2 equals 0, and C3 equals minus 2n, is this guy always a kernel of a point in the Quot-scheme? So this is actually true. This is stated here. So we have a μ-semistable rank 2 sheaf with this Hilbert polynomial. Then we will show that there is some point in the Quot-scheme such that this is the kernel of this point. And how to do this? Let me try to give you an idea. So E being a μ-semistable, it's torsion free. So we have this injective canonical map to its double dual, and we can consider the quotient here. So now, since E is torsion free, the singularity set of E has codimension at least 2. This implies, and since we are in P3 here, I will always work over P3 now. And so the dimension of Q must be less or equal than 1. So we can write the Hilbert polynomial of Q as some AT plus B. So in this case, we can compute now the Hilbert polynomial and the Chern classes of the double dual of E. And so to achieve now our goal in the statement, I claim that this E double dual is equal to the just two copies of O. And so we have the Chern classes of the double dual 0 minus A minus 4A plus 2B minus 2N. To do this, we are going to use Bogomolov inequality, and this states that C1 square minus 4C2 is less or equal than 0. But we know that C1 is 0, so we have that C2 is greater or equal to 0, but C2 is minus A. This implies that A must be less or equal than 0. But remember, A is the leading coefficient of the Hilbert polynomial of Q. Then A must be greater or equal than 0. So these two inequalities implies that A is equal to 0. So what we have until now, that E double dual is reflexive because it's the dual of some sheaf, and the dual of some sheaf is always reflexive. Has rank 2 because E has rank 2. Is mu-semistable because we are assuming E to be mu-semistable, and as I said before, mu-stability behaves well with duality. And we just saw that C1 and C2 equal 0. So our result from Hashon states that then this sheaf here must be 2 copies of O, like we wanted. Then everything is right, like we wanted. E is the kernel of some point in the Quot-scheme. So we have this two-way road in some sense, that kernel in the Quot-scheme is mu-semistable, and mu-semistable with these right Chern classes is the kernel of some point. So before we jump to the next viewpoint, the extensions, let us consider an action in the Quot-scheme here. So I will consider the action of GL2, the automorphisms of 2O on the Quot-scheme. And this action is just given by composition. So we fix up an automorphism here, an element of GL2, and we just do the automorphism and then apply phi. This is just the composition. And using this, with this action and the results that we just proved, we can achieve in this theorem. So we have a bijection between the set of isomorphism classes of mu-semistable sheaves of rank 2 with these Chern classes, and the set of orbits of this action here of the Quot-scheme by over the GL2. So we can study other modular spaces from using this, but I'm not going to talk about this now. And we can jump to the next viewpoint, that is the extensions of sheaves. And what do I mean by this? So this theorem states that every rank 2 mu-semistable torsion-free sheaf with these Chern classes here that we are working, it can be written as an extension of sheaf of ideals with zero-dimensional subschemes of P3. So what do I mean by this? We can fit E in some short exact sequence where this Z and Z prime has dimension 0, and the sum of the lengths must be equal to N. So we have this viewpoint of kernel of points in the Quot-scheme, and now we have this other viewpoint as extension of ideals. So using this, we are going to start studying our modular space that I said in the beginning. So the first thing that we gain for free is by this chain of implications that I said in the beginning. If we assume E to be semi-stable, then E is automatically mu-semistable. And with the right Chern classes, C1 and C2 equals 0 and C3 equals minus 2n, this implies that E must be a kernel of some point in the Quot-scheme. So now we can ask ourselves if the converse is true. So if for every point in the Quot-scheme, is the kernel semi-stable, like we did in the mu-stability? So this is not true in general, but we have this theorem that states a criterion from when a kernel of a point in the Quot-scheme is semi-stable or not. So the theorem says that E is not semi-stable if and only if there is some sheaf of ideals inside E such that with dimension 0, such that the length of Z is less or equal than n over 2. So what we have now is we have this that every semi-stable with right Chern classes is the kernel of a point in the Quot-scheme, but not every kernel of a point in the Quot-scheme is semi-stable. So with the mu-stability, we are also in this bijection between the mu-semistable and the orbits with the action. We can relate the action also here, and what we can prove now is that by fixing a point in the Quot-scheme and let E be the kernel, we can prove that E is semi-stable if and only if the point in the Quot-scheme over the action is GIT semi-stable. And this GIT is in the sense of geometric invariant theory, and it utilizes the Hilbert-Mumford criterion that I'm not going to talk about this. But the point is, this theorem implies that our moduli space is the GIT quotient of the Quot-scheme over this action of GL2. And in a previous work, we studied this Quot-scheme of points, and we showed that using ADHM construction and the commuting varieties of matrices, we showed that this Quot-scheme is irreducible for n less or equal than 10. And since our moduli space is this GIT quotient, and the quotient, if the Quot-scheme is irreducible, then the quotient is also irreducible. So for n less equal than 10, our moduli space is irreducible as a corollary of this guy here. So what we will do now is that we are going to construct an irreducible component for this guy, and this for n less or equal to 10 is the only component of our moduli space. Thus, in some sense, it describes our moduli space. So let us begin with the easiest possible cases, that is the n1 and n2, and then we try to generalize things to n general. So to study n1, we use the first viewpoint, and we can fit E as a kernel of some point in the Quot-scheme, and since n equals 1, this Hilbert polynomial of Q is just 1. So taking cohomologies in this sequence, we get this one. Of course, this goes 1, but we just need this piece here. And now, since we are assuming E to be semi-stable of rank 2, if Chern class is 0, 0, minus 2 now, stability implies that E cannot have a section. So this H0 must be 0. So what we have here is an injective map from this guy to this guy. But this is a vector space of dimension 2, and this is a vector space of dimension 1, and this cannot happen because this map cannot be injective. So this is a contradiction, implying that our moduli space must be empty. And jumping to N2, we use the second viewpoint of extension of ideals. So it can be written in at least one of these forms here. So we put 0 points on the left side, 2 points on the right side, or 1 in each side, or 2 in the left and 0 on the right side. So now studying these cases, we see that the first case cannot happen because this is destabilizing E. We are assuming E to be semi-stable. And now the last case also we don't have to care about, because whenever we have this, and this holds in more generality, whenever we have 0 points on the right side, that is the structural sheaf of P3 here, we can always pass, in some sense, 1 point to the other side. So these two cases, we should not care, and we should only care about this middle case. And studying this case, for example, for P different than Q, then we can compute this X1 and see that it's actually 0. So E must be just the trivial extension, the sum of IQ and IP. For P equals then Q, then we have non-trivial extension. The dimension of this X1 is 3, and we can have non-trivial extensions of IP and IP. And although this is not the trivial one, we can show that it is S equivalent to the trivial one. And what do I mean by this S equivalence? For every semi-stable sheaf, we have this Jordan-Holder filtration for E. And although it's not unique, the graded object is unique. And we say that two sheaves are S equivalent if and only if the graded objects are isomorphic. So just considering this piece here, this gives a Jordan-Holder filtration with quotients IP and IP, because this would be equal. So this is S equivalent to the trivial extension. And the point is, since the moduli space parameterizes S equivalence classes of sheaves, and by these two analyses here, we arise in this bijection between the N2, our moduli space, and the symmetric product of P3. And here we can take the symmetric because the order here doesn't matter because it's just the trivial sum. So what we have until now is that N1 is empty, N2 is in bijection between the sim2 and N2. And we could ask ourselves if for every N, this moduli space is non-empty, or for which values this is non-empty, or if it's all empty. So next, we show that Nn is always non-empty, and we can study N3. First, we do in two separate cases. If N is even, we can always construct a sheaf inside here and show that it's non-empty. But I'm doing this section because I need this lemma to study N3. And this lemma is important to construct a sheaf for the N-odd case. And it states that if we fix a positive odd integer and take E as an extension in some sense in the most balanced case here, that is to put n plus 1 over 2 on the left side and n minus 1 over 2 on the right side, then this E is stable if and only if it's not a trivial extension. So as long as we have non-trivial extensions of these two guys, it's always stable by this lemma. And using this lemma, we can construct for every n some sheaf inside here, showing that our moduli space for n greater than 1, it's always non-empty. And using this lemma, we can study the N3. So to study N3, I will need this lemma here, and this lemma computes the dimension of this x1 of Iz prime Iz whenever these two closed subschemes of P3 does not intersect. So this is just the length of this right side here minus 1. So if you fix a semi-stable rank 2 sheaf with Chern classes 0, 0, minus 6 now in N3, we have these possible cases, putting 0 here, 3 here, 1, 2, 2, 1, or 3, 0. Again, by our theorem that states the criterion for stability of E, these two first cases cannot happen because these guys are destabilizing E. And again, as I said before, whenever we have 0 points on the right side, we can always, in some sense, pass 1 point. And we have only to consider this case here, where we put 2 points on the left side and 1 point on the right side. So we have only to consider this case here. So what we will do now, we will construct an irreducible component for N3. And to do this, we note that if you choose 3 different points in P3, this x1 here has dimension 1 because of the lemma. This is just the length of this guy, which is 2 minus 1. Thus, we arise in 1. What this is saying that for every choice of 3 points here, we have only one non-trivial extension up to multiplication of a scalar. So, and if you note here, this extension here, if it's non-trivial, it's always stable because we are exactly in the most balanced case by our lemma. So choosing these 3 points, there is only one non-trivial extension that non-trivial extension, and this extension is stable. So what we can do now is consider this H here is the symmetric product of P3, and we remove the diagonals to ensure that these choices of points are all distinct with each other. And by what I just said, this H here can be regarded as a family of stable sheaves, because remember, we are in the most balanced cases. And this family has dimension 9, because it's just the choices of these 3 points are open inside sim3. And so by this theory of coarse moduli spaces, this H here gives a morphism from H to N3. And what we can do now is consider the image of this H, which is an open subset inside N3, and we can take the closure inside. To ensure that this H bar here is an irreducible component of N3, what we need to do, what is left to do, is to compute the tangent space of these guys in our family and see if the dimension of this tangent space matches the dimension of our family. And the tangent space of this guy is represented by the x1 of EE. So we have to compute this dimension here. And this is exactly what is stated here in the next theorem. And if we fix a point in the Quot-scheme and let E be the kernel, and if this Q here is in the structural scheme of a closed subset of P3, which is in the smoothable component of the Hilbert scheme of n points, or for simplicity, we can just think of n distinct points of P3, such that this is stable, which is our case in the n3 case, then the x1 is equal to 4n minus 3. So if you put n equals 3, this is exactly 12 minus 3 equals 9. So this theorem ensures that this h bar is an irreducible component of our moduli space. So we can ask now, can we generalize this idea to general n to obtain an irreducible component for n3? And we can try it. So for the n3 case, what we did essentially was take this x1 and take the projectivization, taking the only non-trivial extension of this guy. And so can we do this for general n? So if you try to do this, remember, we need stability, so we should use at least, or try to use our lemma and pick the most balanced case here, because we know that every extension in this case is stable. So we put n plus 1 over 2 on the left side and n minus 1 on the right side. And if you try to compute the dimension of this family now, we have the choices of points, n distinct points. This has dimension 3n. And the dimension of this x1, the choice of extensions, are given by this dilemma that we said before. It's just the length of this guy on the right side minus 1. So it's this guy here. And since we are taking the projectivization, we should remove one more. But this is less than 4n minus 3. So this is not enough to fill an irreducible component of our moduli space. And what we can do now is this. So the guy that we are going to use is this guy. We put only one point here and every other on the other side. So computing the dimension of this family, what we have here is, again, we have 3n by the choices of points. The extension is this guy, the length of the right side here, minus 1. So it's n minus 1 minus 1. And since, again, we are taking the projectivization, we should remove one more. And we arise exactly like the dimension that we want. But the problem is we don't have our lemma now that says that every extension is stable. So what we can do now, again, this h will be some point in the P3, some n minus 1 points in the symmetric product in the choice of extension. Again, we don't have stability anymore. We don't know if every extension is stable or not. So what we can do is to force, taking this HO here, to force stability. And since stability is an open condition, our family would remain with the same dimension here for n minus 3, as long as this HO is non-empty. So what is left to show here, if this HO is non-empty, then we have a family of dimension 4n minus 3 of stable sheaves. And again, this would give a morphism from HO here to NN. We can take the image there and consider the closure, and these have the exactly dimension. So we only have to show now is that this is non-empty. And this is exactly what the lemma says. Of course, I'm not proving the lemma, but this lemma, we give an explicit construction for every n here, and this can be odd or even of a stable here, stable guy inside this. And so this lemma ensures that the existence of a reducible component of our moduli space. So summing up and rewriting in a different form, what we have here is that for every n greater than 2, we have our irreducible component of the dimension for n minus 3, and rewriting this, this component is birational with a total space of Pn-3 bundle over the smoothable component of the Hilbert scheme of n-1 points cross P3. This is the denoting the smoothable component. This is in a more general setting that we did here, but so this is the theorem that we have here. And moreover, like we did before, when n is less or equal than 10, this is the only irreducible component of our moduli space. Thus, it gives a description in some sense of our moduli space. And so this is our main theorem in some sense. We have this description of our moduli space for n less than 10, and we have for general n this irreducible component. So I think my time is over, so thank you.
Thank you, Douglas. Are there any questions? So if there are, yes, go ahead, Amar.
Thank you. Hi, Douglas. It's Amar. So how about higher rank?
Yes, this is exactly the case that we are working now. A couple of months before, we were finishing this rank 2 case, and Daniele asked about the higher rank, and so we started studying this higher rank case. And what happens is we can generalize these results to over any rank, and we have this criterion that of course we have to do some little modifications, but we can have a criterion. We have this bijection between μ-semistability and the action. We generalize most of these results to the rank R case. And this is a more recent project, so I didn't show now because this rank 2 case was more solid in some sense. But we are working now on the rank R case.
Okay, thank you.
Thank you for the question.
More questions? Okay, so let's thank Douglas again.
Thank you.